Okay, welcome all to the online Horowitz seminar. And today we're very happy to have Tal Orenshtein from TU Berlin, Weierstrass Institute and Berlin Mathematical School. Tal will be telling us about rough walks in random environment. Welcome, Tal.
Thank you, Ron, and hello, everyone. I see here many friends, and I'm grateful for this opportunity. Yes, so I'm going to tell you about random walks in random environments viewed as rough paths. So the goal here, so this is a certain program that we have now. Here our goal is to lift invariance principles to the rough path topology. And this has two aspects. One, from the point of view of the path itself. So we would like to understand how does the limiting path look like. So it gives us some richer picture of the path. So this is from the perspective of random walks in random environments or in general particle systems. The other aspect would be the aspect of SDEs or SPDEs, if you want. And here we are interested in what happens when we take non-trivial approximations of the noise in the equation. And here we're interested in the notion of universality. Now, Ron told me that I need to assume that people might not be familiar with rough path at all. So I'm going to tell you a little bit about it, something that you will have in mind. Of course, I cannot tell you too much, but just a tiny bit. So let me start with rough path in general. And here is a motivating question or example. So we're all familiar with Donskoy's invariance principle. You take a random walk, say a simple random walk, or a random walk with a second moment and variance 1, okay? And now you diffusively rescale it. So you define xn to be the diffusive rescaling, where you take your piecewise constant function. Or what you can also do is you can take x tilde to be the linear interpolation of that. And what we know, what Donskoy's invariance principle is telling us, that these two objects are going to converge to the standard Brownian motion in the stochastic topology, right? Yeah. So this is a notion of universality of a Brownian motion, if you want. It tells you that the Brownian motion is universal in the sense that any random walk is going to converge to that. And we don't even care which type of the approximations we are going to take, just because the fluctuations are going to go to 0. The difference is going to go to 0. However, here is a fun fact about stochastic differential equation approximations. So this is addressed in Wong Zakai's paper from '65 and was known before. It is as follows. So let's assume that you have a nice real function f, okay, that is given 0 as 0. And we want to approximate this stochastic differential equation in an integral form. What you can do is you can you know that your first random walk xn is going to converge to the Brownian motion, so you can just take this difference equation here. You subtract, you write, instead of the Brownian motion, you write the random walk, and you know that the solution of this difference equation is going to converge to the stochastic differential equation, where this integral is in the ethos sense, okay? Now, if you want to do the same, but you want to take a different approximation here, so instead of taking this difference, you take the Riemann's tilted integral with respect to x tilde n that we define. And this is a bounded variation, so you can do that. Then this y tilde, the solution of that, will converge to a Stratonovich SDE, so the same SDE, but with a different notion of integration. Okay, so this is well known, but it tells us something. Okay, so it tells us that in some sense, our information about the Brownian motion is not enough. It's not complete to determine which kind of integral we're going to take. It's trivial. In a different formulation for that is to say that the Ito map taking x, the noise here, to y, the solution of the SDE, is not continuous with respect to the Skorokhod topology. However, we do have a notion of universality here, right? Because here it doesn't matter which x you're going to take as long as it has a second moment. And yeah, so and every nice f are going to give you this convergence. It's also here. So it tells you that you have a notion of universality if you're interested in STEs, in integration with respect to a Brownian motion. You need to add some information to the definition of a Brownian motion. Okay, so these are just two specific examples, but this is the starting point of rough path. The idea would be to generalize these ideas or to make a concise theory of how to determine which kind of notion of integration we are dealing with and to get this kind of convergences. This leads us to the definition. I'm going to give you a definition of rough path, where a rough path is going to be a pair of a path, sorry, what happened here? Yeah. So it's going to be a pair of a path and the so-called second level, okay? And it is defined as follows. So it is defined by pairs of times. So you fix a capital T and you look at the interval between 0 and t. And you look at pairs s smaller than t. And then you have two levels for that. The first level is going to be a vector in RD. The second level is going to be a matrix, D by D real matrix. So that the first level here, this guy, is just an increment of a path. And now you want two conditions. The first condition, you want that the path itself, the first level, is going to be an alpha elder path. The second level is going to be 2 alpha elder. Now you can say that, well, it's not a path, so how can you say that it's a 2 alpha elder path? But if you think about it, the alpha elder norm is defined by pairs of times. So you can just define it as is, and there is no problem. So in this sense, we want it to be 2 alpha elder. And what you also want is a connection between the second level and the first level. So yeah, you want that this, so if you fix s smaller than u, smaller than t, you want that this, let's say, generalized increment from s to 2, from s to t, minus the one from s to u, minus the one from u to t, is going to be the tensor product of the actual increment from s to u times the actual increments from u to t. And okay, so, and I'm going to use this notion of tensor product a lot, so just to make sure that you're with me here. These are matrices, so the ijth entry of this object minus the ij entry of this object minus the ij entry of this object equals the ith entry of this object times the jth entry of this object. This is what's written here for every ij between 1 and d. And okay, so this is a rough path. This is called an alpha elder rough path. And the norm is given by just summing the norms. So this is a pre-norm. You need to complete the space, but these are details. And now, morally, the point here is that morally, this generalized increment should be coming from a notion of integration, should be an iterated integral for some notion of integration with respect to z. Okay? If we knew, for any idea of any notion of integration that you have in mind, if you're going to check, you're going to define this iterated integral, and you're going to check this, you're going to see that it's going to satisfy this relation that is called the chain relation. Okay, but the point in graph path theory is that you don't really need a notion of integral, you just need this algebraic condition in order to define an integral. Okay, now if you set both z to be this pair, then the fundamental theorem, but I'm not going to give you all the details, but just the idea is, it's the theorem by Terry Lyons and Massimiliano Gubinelli, and it's telling you that if you have this z, then you can construct this integral of y dz for a large class of y's. These are called the controlled y's that are controlled by z, and the map taking y to z, yz to the integral is continuous in an appropriate, with respect to appropriate norm. And moreover, the Ito-Lyons map taking this, now this more information noise to the solution of this ODE or rough differential equation, if you want, is continuous now. So in particular, if you have an approximated sequence of the noise, the solution to this ODE is going to converge in the half-path topology to the solution of this ODE. Okay, questions so far? Good, so I'm going to...
Tal, I have a question. So go back one slide maybe. So here, when you write the construction of the rough integral, do you mean that it is an Ito integral of a sort, or you're saying there is a construction, you're not telling us the details?
No, there is a construction. That, very good. The information, which kind of integral it is, and that's the main point here, is given by this second level. So if you know the second level, you know which kind of integral you are taking. And the idea is that all the information sits in this iterated integral. So to interpret this, then here, this notion of integration is going to tell you if it's going to be an Ito or a Platonovich or whatever. Okay?
And it can be significantly more general than Ito and Platonovich?
Yes.
Something completely different.
Yes, and this leads us to the next slide. Thank you, Ron. Okay. For example, if you have a semi-martingales, Zn, that converge to a certain semi-martingale Z, and you assume that you have a Stratonovich lift. Okay, so what do I mean? I just take Stratonovich iterated integral, so I assume that I can, okay, like before. So that you have that this pair converges to this pair in the rough path topology, and assume that this second level of the limit is a Stratonovich iterated integral of the first level plus some matrix gamma. Okay, so this is a linear. So this is a linear perturbation of the Stratonovich iterated integral. Then an observation by Kelly is telling us that the solution, the approximating solutions to this equation are going to converge to this equation. So it's the same equation as you would expect, with a correction for the drift. And the correction for the drift can be written and computed explicitly in terms of this matrix gamma. Okay. So in particular, you see Stratonovich and Ito are differed by just by a matrix, right? So just an identity matrix, essentially, scalar matrix. Okay. Good. So, yeah.
Sorry, another question. In the middle equation, if you go back one slide, is it that this is integral against the bold face? Is it? So in the middle, it's also Stratonovich, ordinary.
Yes. Yeah.
No
So
bold face here. I see.
Right. So this is essentially the point that.
So where does it use the definition of the ZST that you defined on the top? Where is it in this statement?
Yeah, maybe I should say that again. Sorry.
I mean, you define the ZST on the top, but you don't use it later on.
Right. So maybe I should. Maybe you should forget about the rough path topology here, because that's not the message. The message is that this is going to converge in the Skorochod topology, okay, to this solution. And the main point that I want to say here is that if you have this kind of convergence, then what you see, in fact, you forget about this rough path thing.
Okay.
You want how would you see it in the usual sense?
Okay. Thank you.
Good. So random walks in random environments, this is more familiar to most of you, I assume, and therefore let's scan it fast. So here we look at ZD, and an environment is a configuration so that on every vertex X, it gives a probability distribution to each of the neighbors. Okay, so omega X, Y are non-negative numbers, and the sum of omega X, Y is 1 over all Y that are neighbors of X. This is a definition of environment omega. And for a fixed omega, we can define a walk as a Markov chain on ZD with the probability, jump probabilities from X to Y given by omega X, Y. Okay, and this is called sometimes the quench law of the random walk and denoted by P omega. And now if we have a probability distribution on the space of environments, we can define the annealed law on the random walk by saying that the probability of an event of the random walk is given by first compute what is the quench probability in the environment omega of that event, and then average over the environment with respect to that probability measure. Okay? So it is also called the average probability measure. Sometimes it's maybe more intuitive. Okay, that's a definition. And now what we are going to deal with two classes of random walks in random environments. One is the ballistic class, and the other is the random conductance model. So let me start with the ballistic class. So for us, these are IID environments. Sorry about that. IID environments with some uniform ellipticity condition, which would tell you that for any X, there is some positive kappa, so that for any X, you can jump to Y with probability at least kappa for every X and Y neighbor of X, almost surely. And then we have some ballisticity condition that we're going to use here, the Snitman's T prime ballisticity condition. You have equivalent conditions that are known now. It doesn't really matter. I'm not going to specify the condition. I'm just going to use some properties of it that I will tell you in a second. But ballisticity, I just want to say already here that it just tells you that you have a law of large numbers, that Xn divided by n is going to converge to some V, which is non-zero. So you have a certain direction, but you have a drift in a certain direction, asymptotic drift. Okay, and it is well known, there are some properties that are well known for these ballistic random walks in random environment. The first one by Snitman and Cerner is that you have a regeneration structure, and yeah, okay. So you have almost surely an infinite sequence of times, tau 1, tau 2, and so on, so that they have all moments. And if you look at the pair of looking what the path did between time tau 1 and tau tau k and tau k plus 1. So this is actually the range of the path between these times, okay? Starting from 0. Okay, I should have, yes, this is starting from 0. So this is starting from 0. This is the increment. It's the path from tau k to tau k plus m. Together with the size of the regeneration time interval. So this sequence is an IID sequence. Okay, in particular, what it tells you that you have a strong law of large numbers here. Xn divided by n is going to converge almost surely to the expectation of the increment of the walk in one regeneration time divided by the expected size of the interval. Let's call this V, this deterministic number. And if you now recenter around V, and take a linear interpolation and rescaling, then Snitman showed that you have, okay, already from this you have you have an invariance principle. So Xn is going to converge to a Brownian motion in the space of continuous functions with the covariance that is the covariance of the increment of the centered walk in the time interval divided by the expected size of the interval. Okay, so this is given, this is known. And yeah, I just want to mention here that you know that if you sample an environment omega, then you see a non-homogeneous behavior, right? You have different probability distributions to jump from in one location comparing to the other. But this tells us that you have this averaging effect or homogenization effect that this, the fluctuation are going to converge to a limit. And this is going to be a Gaussian limit with a covariance matrix, which is in general not the same as in the homogeneous case. Okay. Okay, so the first object, so this is the first object, we want to take ballistic random walks in random environments and view them as graph paths. So what do we do here? We take our x, we scale it after recentering, like we did, and this second level is just going to be the Riemann-Stieltjes iterated integral. Okay, we took linear interpolation. We just take Riemann-Stieltjes integration here of the rescaled path. And this is a theorem with Olga Lopusanschi that we have that in dimension larger or equal than 2 under this annealed law, you have a convergence in the rough path topology of this pair to a Brownian motion in the first level. And in the second level, you see a Stratonovich iterated integral of this Brownian motion plus some deterministic perturbation, linear perturbation. Okay, so plus some deterministic matrix times the time, where this matrix is can be written as the antisymmetric part of this, the expected antisymmetric part of this matrix, where this matrix is the iterated integral of this guy from the beginning of the regeneration interval to the end of the regeneration interval, divided by the expected size of the interval. Where here you see I take an expectation of a matrix, I mean the expectation of every entry separately. Okay, this is just a notation. And the convergence here is in the alpha order rough path topology for every alpha smaller than 1/2. So of course we cannot expect to have alpha equals 1/2 here, because the Brownian motion itself is not 1/2 Helder, it's just alpha minus 1/2 minus Helder. That's any epsilon smaller than 1/2. But the nice thing is that we can go all the way to 1/2. So some remarks about some more remarks about this. So the first remark is that this is an example how you can use this observation by Kelly. You have this gamma here, and if you take an STE approximated by our X bar, you're going to see this correction in the drift. Another remark that I want to make here is that we don't really need this the random walk in random environment, the ballistic random walk in random environment case. This is just an example. What we actually need is that you have a regeneration structure with some moment condition on the regeneration time. So essentially, any path that has this property, you can prove the same result. Yeah, and if you want some examples that you don't have all moments, or which is translate to in the theorem, it's translate to go all the way to 1/2. So if you can achieve, if you want to achieve, okay, if you cannot achieve all moments, meaning that you can get only close to 1/2 up to some epsilon, then you can look at random walks in Dirichlet environments. Sorry. So you can look at random walks in Dirichlet environments with a large trap parameter. So in these environments, you know that you have a regeneration structure, but you don't have all moments. And this is going to be an example for that. Lastly, I want to mention something about this gamma. So this gamma is sometimes called area anomaly. And the reason it is called like that is that it is actually an area. And it is an area of what? So if you look at the ijth coordinate here, and you look between two regeneration times here, okay, and you look what the path did between two regeneration times. So if you now, maybe I should, you know what, sorry about that. Maybe I want to show you a picture here. Can you see this picture?
No, no, we do not see it, Tal. Maybe you need to share the...
Ah, yeah, right. Okay, you see this picture now, I guess. Good. So this is the regeneration structure that you have here. So you have these times here. So of course we need to recenter the path. This is before recentering, but forget about that just for the demonstration here. So if you want to compute this gamma, and let's assume that this is the ith coordinate and this is the jth coordinate, then what you need to do is you need to draw a straight line from this point here to this point here. And then you look at the signed integral that you have here. So this part here, maybe I have another one, yeah. So this part here is going to be positive, this part here is going to be negative. And if you compute this signed area, this is going to be exactly the expectation of that divided by the expectation of the size of this interval is going to give you the exactly this gamma.
Yeah. Okay. Tal, this is the picture in d dimensions, but you're looking at projections on a two-dimensional plane, right?
Exactly.
Thanks.
Exactly. Okay. Good. So I have other things that I want to tell you, and actually a lot. So let's continue. Maybe it's a good point if anyone has questions so far, because we are continuing to the next model.
You may ask questions with the chat or just interrupt with your microphones as I do.
Yeah. Okay. Okay. So let's continue. So for the random conductance model, what we have here we have conductances or weights on the edges of ZD. Okay, so this omega xy equals omega yx, meaning that it's non-directed. And the probability to jump from a site x to its neighbor y is given by the weight from x to y divided by the sum of the other weights between x and the neighbors of it. And okay, so you jump along an edge proportionally to the conductance. This is what I want to say. And from long time ago, already in '83, Kuhneman proved that you have, if you diffusively rescale your process, this will converge weakly to a Brownian motion. It's a very old result, and people were interested and are still interested very much in this model because it has many interesting features. Yes, and let me tell you a little bit about, in general, what people are doing in order to understand these models. Okay, so there are two routes. Essentially, there are two routes that people are considering. One is in order to get annealed results. There is the available Kipnis-Vardhan theory of additive functionals of Markov processes. Now, the advantage of this theory is that you don't need to assume, so it is much more general than for random walk on random conductances, and you can deduce other interesting invariance principles using it. In particular, it shouldn't be just for reversible processes. However, this is limited and you can achieve only annealed invariance principles, at least for the random conductance model, at least for now. And in order to achieve quench result, people have been looking at the so-called cross-cycle spaces. This is a PDE motivated perspective. And where you get more information about how the walk looks like in the environment. Okay, I don't want to go too much to the details. It's too vast to explain in one talk. But let me just mention that there are also a variety of conditions that people are interested in. For example, you can assume that the conductances are not just nearest neighbors, that you can have long jumps, and stationary and ergodic, not necessarily IID, and so on and so forth. Okay, but let me tell you more about results that are relevant to rough path, what I want to report on today. So the first one is a generalization of this, or if you want, enhancement of the Kipnis-Vardhan theory of additive functionals to the rough path topology. So I wrote in one slide everything that I want. So let's go over it. So this is a theorem together with Jean-Dominique Deuschel and Nicolas Perkowski. And it goes as follows. So let's assume that you have a Markov process X that has a generator L, and U is a probability. It's a stationary and ergodic probability measure with respect to L and also with respect to L star. This is a strong condition. If it bothers you, the first example that you can think of is just that L equals L star. Okay, meaning that the process is reversible. And let's assume that we have a function f from the state space to Rd, which is bounded and measurable, that has expectation 0 with respect to this stationary measure. And this is, again, expectation component-wise. Okay, this is a vector, so we just look at all the entries, and we say that the expectation is 0 in every entry. And let's consider here the additive functional of x. So what is this? This is a time integral of f evaluated on the process. And now I'm going to already diffusively rescale that. So I'm going to take the time from 0 to n squared t. I speed up the time by n squared, and I'm going to divide by n. Okay, now I'm going to assume a condition, which is called the h-1 condition, or Kipnis-Vardhan condition, which is written here, but let's just accept that for a second as a condition, some condition. Then the theorem is telling you that if you take your Zn and you take the Riemann-Stieltjes iterated integral of it, this is also bounded variation, no problem, then it will converge weakly in the rough path topology to a Brownian motion in the first level. This is not new. And in the second level, you're going to see a Stratonovich iterated integral plus some deterministic linear correction. Here, this correction is given in terms of, as a limit of a sequence phi lambda, of an expectation of phi lambda tensor with the antisymmetric part of the generator acting on phi lambda. Okay, and phi lambda is some function. What is already to note here that you see an antisymmetric part of the generator here. This tells you that, for example, if L equals L star, then this is 0. Okay, so what you have here is that you have this invariance principle with no correction if your Markov process is reversible. Okay, and that was known already before. The quadratic variation of the Brownian motion is given as this limit, where this is minus the symmetric part of the generator. Okay, and let me just specify what is the h-1 condition that I'm referring to here. So this phi lambda is nothing else but the solution to this resolvent equation. Okay, lambda minus L of phi lambda is F. And the condition is telling you something about this solution. So you want that the L2 norm of phi lambda is going to infinity slower than square root of lambda. And you want that with respect to this, that is called the H1 norm of phi lambda, this is going to be a Cauchy sequence. Okay. This is a technical condition. If you have it, then you have this theorem. Okay. Now, unfortunately, I will not have time to explain how you usually do it, but the way you do it, how you apply the Kipnis-Vardhan theory to random walking random environment, then this is, we do something similar. We're able to use this result here in order to deduce the invariance principle for the random conductance model. And what we get is the following. So if you have an IID and uniformly elliptic conductances, and you have an Ito lift here, which is like the piecewise constant lift like we had on the very first slide of the talk. So under the annealed law, we have the rough path convergence. This one here. First level is the Brownian motion that we are familiar with. The second level is going to be this Stratonovich iterated integral. See, this is an Ito plus this quadratic variation, which means Stratonovich, plus some gamma, where gamma has a formula here, which is a simple formula. It's minus the diagonal metric, so that you see on the diagonal just the expectation of the conductances. And this is an IID, so it's actually going to be a scalar matrix, but it shouldn't. So if we're taking not IID, but just independent and stationary and shift invariant, then it's just going to be an actual diagonal matrix. And I want to just mention that you started from an Ito lift, so you cannot expect to see a Stratonovich integral. So it's not surprising in a sense. But on the other hand, if you would take here a Stratonovich lift, namely linear interpolation, the result is that you are not going to see this gamma, but you will see a Stratonovich iterated integral. This is somehow funny, non-intuitive, but that's the way it is. Okay, so that's one thing that we have. Another thing is to consider cross-cycle spaces in the corrector process. Now, I assume that many of you are familiar with that, and therefore this is just going to be what I'm going to tell you is just going to be to set some notations. And if you don't, then maybe you can get something out of it. I will try to tell you some general strategy to prove quenched functional CLTs. So the way that you prove quenched functional CLTs using this strategy is to find an Hilbert space H of cross-cycle functions on the environment space times ZD. It's called the physical space, if you wish. And cross-cycle, the definition is here, but it is, it's not relevant for the explanation that I have here. So that this H has nice properties. One of the properties that it has, that you can write it as a direct sum of two subspaces. So that if you take the position field, or this function pi, that for an environment omega and a position x, it gives the position x. You want the, okay, it is what it is. And you write your pi as a direct sum of this element from these two direct sum decomposition. And you plug in your process. Then on the one hand, by definition of this pi, your process is pi of omega, the process. And on the other end, you can write it as a sum of these two functions, these two coordinates, if you want, coordinate systems. And now the big issue here, big point here, is that this psi, this element of this subspace, when you plug in the process, you're going to see a quenched martingale. And the rest is what we call the corrector. And what is nice about it is that you can use some analytic tools to prove that this corrector field is sublinear. And when you plug in the process and you diffusively rescale it, then you can show that this vanishes in the limit. So using all of this idea or machinery here, what you can get is that if you diffusively rescale your work, this part is going to vanish, the diffusive rescaling of this part is going to vanish in the limit, and you are going to reduce yourself to proving functional CLT for martingales. Okay, and the quadratic variation of this object is easy to analyze. So that was, in a nutshell, how one would prove a quench invariance principle in the classical sense. So let me tell you what we did in this direction. So in joint work with Johannes Bäumler, that I saw him here, and Noam Berger and Martin Slowik, we have two things that we're doing here. First, we consider, we prove an annealed result, but here we have much more general conditions. For example, we allow the process to have long jumps and only first moments for the jumps, and some mild regularity condition except for that. Okay, what I want to mention about this result that I found interesting is that you know that this corrector, as I mentioned, if you rescale it effusively, it will vanish in the limit. But its iterated integral is going to converge to a non-zero linear function. And it's just going to be the second moment of the Hilbert space norm of this guy, of this corrector coordinates that we have here. So in this way, we have another formula for that area anomaly that we had from the Kipnis-Vardhan theory. Okay. Another thing that we can get from this using this perspective is as follows. So the classical quench invariance principle is known for more than 15 years now, and a recent result that by Paul Dario, who's now in Tel Aviv, I think, is telling you the following. So if you take, if you consider the random conductance model on ZD with D larger or equal than 3, and IID nearest neighbors conductances with values that are either 0 or in a compact interval away from 0, okay, then the corrector can produce a stationary corrector, and this corrector has Hall moments uniformly in space. Okay. Now, also, there are available quenched ETH kernel bounds. Okay. Yeah, I've been writing some references here. I'm not mentioning everyone. So what we can do using these ETH kernel estimates together with the result by Dario is to get the quenched, you have a uniform bound on the pth moment uniformly in time. That's the point. You can get a p moment which is uniformly bounded in time, quenched, so almost surely. And after you have this, then everything is essentially a piece of cake, because you have just, it's a nearest neighbor jump. So you can translate this estimate also for the martingale part. So you have also all moments for the martingale part, and then some work are going to give you that this is, it's going to give you the quench result that you're after. And yes, okay. So let me summarize what I told you today. So yeah, I told you about our program that to lift the invariance principle for the rough path topology. It has aspects of approximations of SDEs and give you some richer understanding of the path. We discussed some ballistic random walks random environment, which is the non-reversible case, where we identified the area anomaly in terms of a stochastic area in a regeneration interval. We have a Kipnis-Vardhan theory in the rough path topology, and you get no area anomaly if the process is reversible. We applied it through the random conductance model. There we get a correction for the Ito rough path, but no correction for the Stratonovich one. And I want to mention that this method, the Kipnis-Vardhan method, extends to many other models, not necessarily reversible. For example, periodic diffusions. You can find that in the paper. The last thing that I mentioned was regarding cross-cycle spaces, a strategy there. We see an area anomaly in the Ito case, which, okay, we had that already, but we can identify it in terms of the H norm of the corrector. And Yes, and the point there was that it holds quench whenever the corrector has enough moments, and this is not completely written yet, but I strongly suspect that 2 plus epsilon moments for the corrector should be enough. After it will be completely written, we will know if that is the case or not. Or we would know if we could prove that or not. Okay, that's it. Thank you.
Okay, thank you, Tal, very much. So questions, please. You may unmute yourselves and ask on your own.
So Tal, hi. I actually had a question. In your non-reversible model, I didn't catch, was it a quenched or annealed result?
Annealed.
Annealed. And what about quenched?
It's a very good question.
Can you go back to the slide, Tal, so we'll see?
You had a lot of patience.
Sorry?
Right.
No, I sent you a chat question. You just didn't
I'm sorry. I'm sorry. I didn't see it. Okay. Yeah. Here it is. Yeah, so it's a good question. The short answer is that we don't have it. I'm discussing this with Noam and also with Johannes. We are trying to get it with different direction. One direction that we are trying to consider is your paper with Noam, trying to push it, push your method further to this, to this settings. The problem is that this iterated integral, it has a lot of inferences, so you cannot really.
But at least in the case where, let's say, is a non-nestling case in which you have a deterministic positive drift always, that should certainly be the case. Because then you can define the regenerations in terms of something auxiliary that has nothing to do with the random walk.
Okay, yeah, okay, let's say that I believe that it should be correct quenched.
Okay.
Definitely. But okay, thank you. I will think about it.
Okay.
Other questions, please? Tal, I had another question. So I'm not very used to the rough path topology. So I understand that you upgrade the convergence results and you get more information about the path in the limit. Could you give us an application, like the standard application? What is it that you now know that is that you wanted to know?
Okay, so yeah, it's a tricky question actually, because you see, if you have a continuous function and you plug inside a process, then you already have, and you want to approximate an SDE, then the best thing would be just to plug the function on the random walk. You don't need to solve this equation. This is not a good approximation. Then it gives you no additional information. The example that you can apply these theorems is just take the iterated integral. So take the iterated integral of x with respect to itself. So there is a non-diagonal element, and this is not determined by the approximation. So it depends on the approximation. So you cannot say anything about it. It has no limit unless you specify what kind of approximation you are taking.
Very good. Now I get much more. Thanks. More questions, if any? Okay, if no more questions, let us all unmute ourselves and give a big hand to Tal. Thank you very much. Okay, and next week we'll have Christophe Garba from the University of Lyon. I'll send an announcement. Thank you all for coming. I'll stop the recording, but I won't end the meeting. Maybe if somebody wants to catch up with Tal, ask more questions, you're welcome to do it.